Okay, here's my second example for the phase plane. So here I've got sort of a nonlinear spring. So if you look at it, the equation is x double prime plus, in brackets, 1 minus x squared x prime plus x equals 0. So the spring constant is 1 and the damping constant is 1 minus x squared. So you think about that, if x is small, it's a genuine damping constant if x is less than 1, and so it'll damp the spring. And if x is greater than 1, it's an anti-damping, and so it'll speed up the spring, the mass. Okay, so what you should predict is that for small values of x, it'll stay small and it'll be a bounded solution. And in fact, it'll go to 0 as t goes to infinity. And if x is large, then x will remain large, and in fact, it'll go off to either plus infinity or minus infinity, depending upon whether x is positive or negative. Okay, so let's go and check that out. So I'm going to evaluate the cell. Okay, I'll be back after I share that with you. Okay, so here we're back, and so hopefully you can see the phase plane here, and let's see what happens. So I predicted that for small x, it'll stay small. Oh, there it is, it's bounded. So we see the arrow pointing inwards, and it's going towards 0. So the limit as t goes to infinity for x is 0. And we see, in fact, that there is some kind of boundary here, and that's probably going to mean that there's some periodic solution. So anything that starts inside there stays inside there. And if you go up here to this button here, I don't know if you can see that, but it'll give you the time plots. So you can do that on your own. But what happens when we are outside this region? We see that it goes off. Here it goes off to infinity, and on this one here, it goes off to negative infinity. Okay, so as predicted, we see that that behavior. Okay.